Okay, next syllabus point is asking us to investigate the processes used to analyze structure of organic compounds. With these, I was going to say 3, but there's 4 techniques in there. 2 are very closely related though. So that's going to take up the most of this chapter. I think that's the end of the chapter, but it's a long path. Okay? You're going to have to learn how these things work and what their output is and how to interpret that output and find out some structures. Alright, so let's just start with a few general slides of overview. They're all spectroscopy techniques, and excuse me, I think if I haven't said it before, I'll talk about it soon. Well, I'll do this first anyway. So, most of these techniques, in fact all of these techniques, use a form of energy to interact with the matter and produce some kind of spectrum. Okay, so I've got a few images of the machines here. Okay, this one's an NMR machine, which we'll learn about later. This one here is a mass spectrometer, and it also has a gas chromatograph attached to it. And this one on the end is an infrared spectrometer. So infrared will be there. Mass spectrometer is this guy. And the NMR machines look like this to various sizes. Okay. Here's a chart that I put in now, but I think it'd be better to come back to this. Okay. It's a nice summary of what each of these techniques do, what it finds out about the organic structure, their advantages and disadvantages, okay? And down here we've got UV vis spectroscopy. The syllabus puts the UV spectroscopy with the organics as well. We touched on it a couple of chapters ago. Yeah, so go back and look at that. So we won't go into it in this chapter. So just a reminder about the electromagnetic spectrum, which is the range of energies and wavelengths of electromagnetic waves, okay? It'd be important to be familiar with the relative energies and frequencies. So we've got UV light. We talked about UV light a bit in UV vis spectroscopy in the last chapter. And beyond there we've got infrared in this direction, so longer wavelengths, lower energy, infrared, and we're going to talk about that in infrared spectroscopy. So infrared does a special thing to molecules. And up above light we've got UV, ultraviolet, so we use that in UV vis spectroscopy as well. And right down the bottom here, in the lowest frequency, longest wavelength, we've got radio waves, and they come into NMR. Okay, so here's a nice diagram and reminder, except the animation doesn't work in a PDF here, of what happens to molecules and how they interact. So on our little graph here, what we've got is our y-axis is different energies, and what they're trying to show is what different forms of energy do to molecules. Okay, so here's your ionization energy roughly, and so that fits, so you can compare what different light does if the light has more energy than ionization energy or less. Okay, or is it ionizing radiation? Is these ones up here? So ionizing radiation or non-ionizing. Okay, so you can see we've got ultraviolet, and ultraviolet has relatively this energy within a range. So most of it has non-ionizing, but there's a slight amount of high energy ultraviolet right up in the high frequency that does have enough energy to cause radiation, to cause to cause ionization. Okay, so you're promoting electrons away, and you're making these atoms become a bit more reactive then. Okay, visible light, the range of it here is below ionization energy. What visible light does, and most of UV, is just promote electrons from lower to higher orbitals, okay? And that's what UV spectroscopy is. It's all about looking about absorption when electrons jump up orbitals, okay? So this is UV vis kind of range. That's what UV vis, we're looking at electron level changes. Now infrared, you can see, has a lower energy again, okay, longer wavelengths. It interacts with matter, looking at vibrations, okay, so stretches and stuff like that. So stretches and what's the other, bends and stretches, okay, so looking at these, go in and out, stretches and in and out and stuff like that, doing a wiggle but not actually breaking bonds and not promoting electrons, just moving and wiggling the molecule, okay? And right down the bottom here, you've got microwaves, very, very small energy, definitely non-ionizing, and what they're going to do is rotation and torsion of molecules, okay? So that's what NMR is. It's looking at rotation and torsion. So this is IR spectroscopy, and this is an NMR. And the other one that we're missing is mass spectrometry. It's looking at ionization and doing stuff with it. Mass spec, we want to cause ionization and stuff happens from there. We'll get to that soon, okay? We'll get to it real soon. We'll do that now. Okay, so the rest of this video, I'll just go through the mass spectrometry section. So mass spectrometry is a technique that allows for the identification of a molecule and its structure by deliberately making the molecule unstable, and from being unstable it falls apart and does certain reactions and you get fragments, and the mass spectrometer looks at the resulting fragments. Okay. A mass spectrum is produced, and this is a mass spectrum here, and it can be used to analyze and determine the structure of the fragments and then rebuild those fragments into knowing the original structure of the molecule. Okay. Mass spectrometers are very widely used in all chemical industries as well as in forensics. Okay, many different uses out there. So here we go. So mass spectrometers have been used to determine nerve agents used in warfare. So back a few years ago, I think probably about 5 or 6 years ago, where Syria was having a civil war, there was nerve gas released in the populations, and scientists actually went in with very small mass spectrometers of these instruments and measured the residue left behind and determined that the source of the chemical nerve agents was actually from their own government. So small suitcase size ones of these. This one here is a typical one that you see in a lab, and it's hard to get a perspective on that, but that's about 1/2 meter tall by about 3/4 of a meter long, and it's about 1/2 meter deep. Kind of decent box size. Not a good description. Okay, so you can get smaller ones. They're not quite as they're more expensive, of course, but not quite as adaptable. Okay, also NASA probes. So for example, the Curiosity rover is still going strong on Mars. It has several mass spectrometers on it, some of it using X-rays, stuff like that, all to analyze the composition of rocks and determine what organic molecules are there, and looking in particular for organic molecules that suggest that life was once present on there. Another type of example is you can look at the molecules in wine. So wine science is very big. It's a big industry, and there are scientists who use mass spectrometry to look at what gives wine certain flavors, and analyzing it that way and comparing it to human sniffers of wine and tasters of wine who are pretty good. So putting the science to it and finding out what these molecules are. You can find illegal traces of drugs from surfaces. So airports use rudimentary mass spectrometers, with a wand kind of thing. lots of different applications. I've used them in research back when I was doing research as well. I can go on many tangents here. Okay, how will mass spectrometer work? I'm going to use the diagram from the textbook and just take you through section by section in, I'm going to say, chronological order, or the order that it goes through the instrument. So up this end that I've drawn the box up, this ionization end. Remember how I said ionization, mass spectrometry starts with ionization. So what you do is you get a sample of a pure substance. You can put a mixture in there, but you just get a confused output. But put a pure substance in. It's injected, vaporized sample, so it's injected into the instrument, which is the whole instrument in here. The whole tube is held down near vacuum, so it's been pumped out full of all gases. And so a sample gets injected in, and because there's near vacuum, it gets vaporized. Okay, so it turns into a gas state because there's little to no pressure in there. Okay, now the injectant, these type of things here, this is the injection port. You can use like a syringe to inject it in. You can also, a lot of research in the last 10 years has been, instead of us directly injecting a prepared sample, is open air sampling, where we use a needle or a probe to directly go into a sample at different points. Anyway, so usually most samples are just put into a solution of some kind and injected in there. Okay. What happens here at the electron trap is the ionization. So we've got an electron trap and electron gun. So it's actually shooting electrons, and it's just shooting electrons, just like in physics with one of the, you know, the cathode ray tubes kind of thing. Okay, so our sample passes by the electron gun. Okay, so a sample from the textbook here is M. We shoot an electron from it, and what it ends up doing is the original electron that shot it comes away, and we shoot off an extra electron. So now we have this particle here that's resultant that we've labeled M plus with a dot on there. Now the plus is just a positive charge. We've lost one electron, so now we have a positive charge. And the dot, remember, is the symbol for a radical. We have one unpaired electron there, okay? So it's quite unstable and ready to react, okay? So it's a positive ion, and it's a radical. So it's ready to react with stuff near it, but that's why we evacuate the tube, though, get rid of all the gases around it. So it finds it hard to react. Okay, so we've got an unstable little thing here that's a positive charge and a radical, and it's going to travel along the tube. Okay, so it's both reactive and unstable, and a proportion of this M plus radical will decompose and fall apart into fragments. Okay, now it depends what the original thing is to what fragments it will make and how many fragments it will make. Okay, but it will try to seek the most stable. Okay, the enthalpic drive there. It will want to get rid of its energy and go for the most stable fragments. Okay, and so what ends up happening is it can and it will split apart into different fragments. And so the thing with this is some fragments will keep the positive charge, and the other fragments will take the unpaired electron and be neutrally charged. Okay, so you're going to get some cations still alive, and you're going to get the radical going with other fragments. Okay, so one will inherit, I like the word inherit, the charge. The others will inherit the radical. Okay, only the charged species, which is either our original cation radical or one of these charge fragments, not the other one, will then interact with a magnet. Okay, so we got, after this, we're going to shoot it towards a magnet. Okay, the only things that will the magnet will only interact with a charged thing. Okay, so what will happen is the radical that is uncharged will not respond to the magnetic field, and it has no charge, and it literally hits the wall, and That's why it's curved, okay? This tube is curved, and the electromagnet is curved, so that the non-charged particles hit the wall, okay, and they can condense down and they can drip out, okay? So we're deliberately taking out, and we're only keeping the charged things. The charged ones will follow a curved path. Okay? Okay, so at this stage, after the electron pump, we have a mixture. We have the charged particles and the uncharged. The charged ones will interact with the magnetic field of the electromagnet. And we can do this. Do I mention it on the next slide? I probably do. Okay, so the charged particles are deflected around the curved path surrounded by electromagnet. So the electromagnet is forcing the charged things around a curve. So the electromagnet makes a magnetic field for the charged particles to curve through. Okay, you can see that these beams of iron will either be focused in different strengths. So some will have different curves. Okay. And that depends on a couple of things. That depends on their charge and their mass, and we'll go through that here. Okay? So the charged particles will travel in a curve in the magnetic field. The radius of their curvature, like this red one here's got a short radius, and this blue one here's got a very long radius, is proportional to their mass to charge ratio. Okay? So it depends on their mass, or their molar mass, how big they are, molar mass, and it depends on their charge. Is it +1? Is it +2? Is it +3? Okay. But in this course, we'll just keep it simple, and we will assume that all of the charged cations coming through just have a charge of a single positive. Okay. So if they just have a single positive, it's not their mass to charge ratio. The path or the radius is determined by their mass, okay? So the heavier things will resist curvature, and they'll have the widest one, and the smallest particles will have the tightest radius, okay? And so what we're ending up here is a spectrum of masses. That's where the name comes from. This one's a GIF also, and it swings back and forth. So you've got a visual spectrum representing a mass spectrum there, but what the GIF shows is with a permanent magnet you can change, well, it's an electromagnet, but you can change the magnetism of it, and you can swing this path back and forth. So you can see the blue stuff at one end, and then later on you can see the red stuff later on. Not that it's coloured that way, it's arranged by mass. You can see the light stuff, and then you can range to the heavier stuff. Alright. So the strength of the electromagnet changes through time, and what we end up getting is at a single point, our detector, at sometimes we're getting the lighter stuff, and at other times we deliberately change it to get the heavy stuff. We get so this detector just does a count by their mass, and what ends up happening is we get one of these mass spectrums. And so the count is this, where it calls it relative intensity, this Y scale, and this X scale is a mass to charge ratio. Okay, and because I said in this course we'll just deal with charges of +1, this is essentially a molar mass range for the x-axis. So the 20, 40, 60, 80, 100, and 120 that you're seeing, you can treat as 20, 40, 60, 80, 120 grams per mole. Okay, and remember, that isn't the molar mass of the whole particle. They're the molar masses, or the mass to charge ratios of the fragments that are coming through. Okay, I'll talk about that more. All right, I might talk a little bit more about it here. See how you've got different relative intensities. Okay, you can see one's really big and you can see others are really small. What ends up happening is the machine automatically detects the most abundant and sets that to 100%. And then scales the intensity of every other fragment mass that it detects according to that. Okay, so the maximum for these will be 100, and this one I'll talk to in a second, but we call the base peak. Okay, and all that is the most stable fragment that comes from the molecule that broke apart. So this one had a lot of different fragments, but the most stable fragment had a mass of about 42 mass to charge, or 42 grams per mole. Okay. Now, there was some smaller, there was some larger, but you'll see that 100 is the largest here. So 100 mass to charge. There's no other peaks after that. So it's saying that the largest fragment we saw was 100 grams per mole. And we'll come back to that in a second. That also has another name. It most likely is, and for our case, the parent peak. And we'll get to that. What is the function of the magnetic field in a mass spectrometer? Past paper exam question here. It detects the mass of particles. No, the detector detects that. It deflects the stream of charged particles. It sure does. All right, let's check the other ones. It excites electrons to higher energy levels. No, we don't even do that with mass spectrometry. We ionize it completely, okay? And that happens earlier. That's nothing to do with the magnetic field or the magnet. It produces a stream of electrons that bombard a sample. No, that's the electron gun produces a stream of electrons. So definitely be there. It deflects the stream of charged particles. Okay, I might leave it here and we can change it up to separate.